Hello and welcome to York Observatory's weekly Teletube broadcast, the online astronomy and astrophysics program written and presented by the students, faculty, alumni, and friends of York University. We're broadcasting live from the AICO Observatory located at York University in Toronto, Ontario, Canada. York YouTube broadcasts every Wednesday night at 7:30 p.m. local Toronto time. For any questions or comments you have of our past shows, or if you have suggestions for future topics, please send us an email at observe@yorku.ca. You can always connect with us on Twitter or Instagram with the handle @YorkObservatory and Facebook at AICO Observatory. We would like to inform you about the opening and call for applications for the Summer 2023 Astronomer in Residence program. This program is a collaboration of the AICO Observatory with Killarney Provincial Park to host astronomers in a certified dark sky site of Killarney to lead in-person presentations and shows using the park's observatory. To learn more about the program, its requirements, and the application process, visit our website at yorku.ca/science/observatory/air. Good evening, everyone. I'm Cam, and I'll be one of your hosts this evening, along with Nakul, Pouria, and Maheen, who's taking over Sina's part. Tonight, we have Dr. Armour as our special guest. Professor Armour will talk a little bit about impact structures here in Ontario. But before we get started, I would like to mention that the observatory at York campus is in Toronto, and we would like to welcome to all show and acknowledge the traditional land that our telescope is on. The observatory acknowledges its presence on the traditional territory of many Indigenous nations. The area known as Toronto has been taken here by the Anishinaabe Nation, the Haudenosaunee Confederacy, and the Huron-Wendat, and also the Métis. It is now home to many Indigenous people. We acknowledge the current treaty holders, the Mississaugas of the Credit First Nation. Our stargazing and astronomical efforts showing the long history and current practices of astronomy for this land. The observatory looks forward to continuing to learn and revitalizing our knowledge in this area. I am now giving it away to my colleague Pouria.
Thank you so much, Camilla, and welcome everyone. Before we get started with our main show, we want to give you a little update on what you can see this coming week. We have Venus, the Moon, and Mars visible in the night sky. In the west, after sunrise, we have constellations Perseus, Gemini, Taurus, Orion, Camelopardalis, Auriga, Cancer, and many more other constellations. The moon is in a waxing crescent phase. On April 20th, the moon was in the new moon phase, and on April 27th, which is tomorrow, the moon will be in the first quarter phase. First, we have our moon, which as said before, is in waxing crescent phase, which means that less than a quarter of the surface of the moon will be visible to us. If the weather cooperates with us astronomers on Earth, you can catch a good view from just about anywhere when the skies are clear. Visible planets in the night sky this week are Mars and Venus. Mars is the fourth solar system planet from the Sun and the last rocky planet of the solar system. This planet has some close similarities to Earth, such that Mars completes its rotation around itself and has its day every 24.6 hours. A fun fact about Mars is that a day on Mars is called a sol, meaning solar day. Mars would be hard to see with a naked eye, but it will be quite close to the moon when you are looking into the sky. Next visible planet is Venus. Venus is named after the Roman goddess of love and beauty. How cute and adorable, but the planet is far from being adorable. The planet's surface is covered with a hot, toxic atmosphere. The reason that this planet is so hot is because of greenhouse effect. Carbon dioxide in this Venus atmosphere traps the heat inside the atmosphere, increasing the temperature and pressure as the result. Now I have no idea what is lovely about this planet. How you can see Venus with a naked eye after 2030, after 20 and 30 minutes. It will be very bright, so it will be easy looking at it. And lastly, we have the constellations. In addition to our circumpolar constellations, we also have Aquarius rising before the sun around 4 a.m. And if you're up early, you may be able to catch some of the Eta Aquarius meteor shower, which will be peaking next week on May 4th to May 5th. The Eta Aquarius meteor shower is usually active between April 19 and May 28th every year. This is one of 2 meteor showers created by debris from comet Halley. The Earth passes through Halley's path around the Sun a second time in October. This creates the Orion meteor shower, which peaks around October 20th. So that's all for what's up in the sky. So now that we are finished, I will pass it to my colleague Nakul, who will introduce you to our guest speaker tonight. Nakul, please go ahead.
Hello everyone. For today's Teletube episode, our guest speaker is Dr. Mary-Helen Armour, who is working on the impact structures. She did a master's in physics and astronomy at York University. Her PhD in geophysics, which is on using near-surface geophysical investigation of known and suspected impact structures in Ontario. She currently teaching at the York University in a division of natural science. We are glad to have you for our today's episode. Dr. Armour, please go ahead and take it away.
Thank you, Nakul. So I will share my screen here so I can bring up my presentation, hopefully. So as Nakul said in the introduction, I did my PhD in geophysics, looking at sort of the subsurface structure using geophysics of impact. So I focus mainly on impacts in Ontario. One in particular here, you can see this is actually Holliford impact structure, and there is a dairy farm and dairy farmers that own the majority of the land on which this crater sits. So they have named their farm Crater Farm. Now, most of us are familiar with seeing impact craters on the moon or Mars, or maybe even Mercury. But the truth of the matter is actually there's quite a lot of impact structures on Earth. They're just much harder to see because of sort of what happens on Earth's surface. Typical of what we might see on the moon here is Clavius. This can actually be seen with binoculars. This is one of the largest impact structures on the moon. And as you'll see, it's not a single structure, but it has been hit multiple times. So there are smaller craters within the larger one. So generally here on Earth, these are recognized impact structures on Earth. This is going back to 2000, this map. So it is missing a couple. But the major ones I'm going to talk about in Ontario are all represented on this map. And there are a number of these kind of maps available where you can sort of find out a lot about where impact structures can be found on Earth. Now, so what really is an impact crater? It's something we have to understand. And sometimes I talk about crater as where Earth meets sky, because this is where sort of astronomy impacts on Earth and starts to affect the geology. So impact craters are really where geology and astronomy will intersect. And impact craters will form when an asteroid has sufficient mass and sufficient velocity that they pass through Earth's atmosphere almost unchanged. They will hit at high velocity on the surface. It's sometimes referred to as hypervelocity. And the energy of this impact, of this sort of contact, actually evaporates most of the impacting asteroid and digs out a very large hole with this kinetic and heat energy. In large enough impacts, it actually melts the underlying rock. The key thing about a true impact structure, though, is you find very little remaining of that bolide, as we refer to them, or the impacting body. The original sort of asteroid, for the most part, is destroyed in the process. So what we're seeing is then how the energy of this process has sort of resculpted the surface. So when we look at impact craters, we tend to talk about them in two types. This is from the Lunar and Planetary Institute. And the two main types of crater we see here on Earth are simple impact craters. And as you can see, they're pretty much just a hole that has been dug out of the ground. There is some fallback material that we talk about as breccia. The underlying rock is fractured, and you get some material that's thrown out of the crater. Once the crater gets to be more than a few kilometers across, it starts to develop what we call complex features. The key one of these is this uplift at the center. And if the crater gets even bigger, you'll actually get sort of a series of rings, not just sort of a single ring. Probably the best known crater on Earth these days, of course, is Chicxulub, the one that's associated with the extinction of the dinosaurs. And that actually is a complex crater. So where are these craters here in Ontario? So I have most of these mapped here. The only one that's kind of missing is Slate Island. If I wanted to get this one on the map, it would have made all the others a little bit too close together. But we have Slate Island, that's near Thunder Bay. We think the impact happened about 450 million years ago. By far the largest impact structure in Ontario, and in fact in Canada, is Sudbury. We think this impact occurred about 1.85 billion years ago. So this is quite an old impact. Sudbury is actually the second largest known impact structure on Earth. And I'll talk about it a little more in the next slide. Very, very close to Sudbury is another crater called Wanapite. We think this impact is only about 37 million years old. The two other recognized structures in Ontario are Brent, which is actually right in Algonquin Park. There's actually a Brent hiking path so that you can go and see this crater. The other recognized one is Holliford, which I had on that first one. And this one actually is about 40 kilometers just west of Kingston. And Holliford is a simple impact crater, and so is Brent. The situation with Wanapite isn't as clear because it's sort of in that size range where it's getting to be it's somewhere between simple and complex. And Sudbury is definitely a complex impact structure. There are also 3 other suspected structures in Ontario. And what this means is we have a lot of geophysical evidence that suggests they are impacts, but we don't have the detailed geological rock structures that are generally considered the definitive evidence of an impact. 3 of these are Charity Shoal. This is actually right in Lake Ontario, on the very near to where the border between Canada and the US is. I've actually done work on this particular structure. Skeleton Lake is up in the Muskokas, quite close to Huntsville. That actually is a lake. And there's a third very interesting one that's here submerged on the bottom of Lake Huron. It's known as the Can-Am structure. This one is actually quite large. It probably is a complex impact structure, whereas Skeleton and Charity Shoal are likely simple impact structures. And you can see with Skeleton and Charity, we do think they are probably in the same age range as Holliford, which is at least 600 million years old and maybe is up to about 1 billion years old. Brent has been studied a little more in detail, so we know its impact age is probably around 400 million years ago. Right? So when we look at Ontario, we actually don't see any really, really recent impacts. Probably the best known recent impact, of course, is the one they were using on the opening slide for this talk tonight, which is, of course, the Barringer Meteor Crater. And actually, the Barringer Meteor Crater is probably very, very close in size to this object, to the structure at Charity Shoal. So Sudbury is actually a very interesting impact crater. It did happen almost 2 billion years ago. And although we tend to think of impact craters as circular, and they certainly will be when they first form, the interesting thing about Sudbury is it happened so long ago, there has been subsequent geological activity that's actually compressed it into this long, straight shape. So Sudbury originally, we think, was an impact structure up to about 250 kilometers in diameter. It's a little unclear because it has been so deformed and distorted. But we have the Sudbury impact structure. And the key thing about the Sudbury impact structure that's very, very interesting is because it was so large, you had a very large melt. You can see over here in this figure I have on the left, it produced what we call a melt sheet. The sheer energy of the impact would have melted the underlying geology. And that's actually why there are so many mining resources in and around the Sudbury area. So the Sudbury impact is actually what's created those very rich mining resources in this area. That's also partly why we understand the Sudbury impact crater so well, because there's been a lot of geological investigation in this area because of the resources. So when something hits that creates an object the size of Sudbury, the thing, again, despite the fact that this bolide, this impacting asteroid, is probably, hundreds of meters in diameter, if not over a kilometer, it's still, the sheer energy evaporates it, fragments it. There's almost nothing left. You have shock waves that travel. Because of the geological organization of Earth's tectonic plates, Sudbury probably impacted actually into water, which would have generated a massive tsunami. Okay? So now if we look in the cross section, here's sort of the actual city of Sudbury, and the impact structure is just outside. There's this sort of massive melt rock, and this is really what is responsible for Sudbury being a mining complex. Interestingly enough, if we look around the world, the impact structure that is the largest in the world, Fort in South Africa, is also actually very rich in various types of mineral resources. And that's probably a direct link. Right? It's covered here a little by the video, but right up here in this corner, interestingly enough, is Wanapite. It's currently a lake. But it is recognized as an impact structure as well. So these two are very close together, but this is entirely coincidental because there are probably hundreds of millions of years between the time when these two impacts happen. Now, an object I've done some study on is the Holliford impact crater. And what's really great is with high tech being the way it is, we can now get this really beautiful picture that I have here on the top right, that sort of shows the remnants of the crater. This is sort of, the elevation is exaggerated so much, but we can see that here's the sort of bowl shape of these impact structures. And Holliford and Brent and quite a number of others across Canada were actually discovered in sort of the late 1950s, early 1960s, when the Dominion Observatory undertook a series of searches and aerial photographs to look for these potential sort of circular structures on the surface. Holliford was one of those that was identified, as well as Brent impact structure. And so we see at Holliford, this is sort of modern technology giving us a really good picture of what's still sort of what the surface expression is. You can see here in this bottom image, this is very much what the original sort of investigators would have seen when they were looking for these impact structures. And because these structures are so old, we actually don't see a lot of them. The other problem, of course, at Earth's surface is vegetation tends to cover things, so it makes it much more of a challenge to find impact structures on Earth, which is why we use a combination of surface topography, aerial photographs, geophysics, to try and better understand these things, because the situation is much more complex on Earth than, say, those lovely images we have of the moon. Now, one of the ways we do confirm that something is an impact structure is we drill boreholes. At Holliford, 3 boreholes were drilled. And so this gives us a rough idea of what has happened. Now, because it is so old, it has been filled in by later deposits. But underlying these deposits in the boreholes, we can clearly see the breccias that are sort of the material that's broken up and deposited in the crater that overlies the basement, the pre-existing rock. Right? So these impact structures do have a very significant effect on the landscape. Holliford in the past seems to have undergone periods when it was a lake and later filled in, and now, of course, it is still a low depression. So these structures over time do change quite dramatically. Now, the 2 objects I probably know the best are these 2 suspected ones, which are Charity Shoal and Skeleton Lake. Charity Shoal is very similar in size to, of course, the Barringer meteor crater. Now, what we're actually seeing on this image on the right, this is a very detailed bathymetry. And the thing is, because Charity Shoal, we think, is at least, 500 million years old, we're not actually seeing the crater itself. We're seeing the later limestone that's kind of been draped over top of the existing crater, but we still see this sort of projection. Right? In the case of Skeleton Lake, this is, again, we're using geophysics. In this case, this is bathymetry that allows us to get a sense of what the crater is like shape-wise. Okay? And in fact, if you go, if Opal Island, in fact, in Skeleton Lake, does have a few outcrops of breccias still existing. Others have been found in Tomlin Bluffs in the past, but heavy cottage development has made this very difficult to locate again. But both of these objects are suspected to be impact structures. And one of the main reasons we do suspect is from the geophysics, which is the kind of thing I do. Now, these are actually magnetic diagrams. So they show over where you have this part of the ring, it extends down here, although it's not quite as obvious. These magnetic highs indicate sort of the presence of this upraised rock and this more magnetic structure. In fact, in Charity Shoal, the magnetic divergence is actually great enough that people navigating in that area will see sort of fluctuation in their compasses when they cross over the structure on a boat. The other thing being is Charity Shoal wasn't originally recognized as potentially an impact crater, but there has been on the sort of western side, or sort of the eastern side of the crater, it has been known to be upraised because there's actually a lighthouse there. So part of the structure has sort of been recognized for decades, but it wasn't until about the late 90s that they realized it was a complete circle and likely, a strong potential of being an impact structure. Skeleton Lake was originally found in some of those early Dominion Observatory surveys, and later geophysical data, both gravity and magnetics, also suggested it was an impact structure. So again, this is work I've done where we've gone out and taken magnetic field readings. And again, you can see, particularly at the northern end, there's a distinctly circular rim. This is also quite visible when you're actually on Skeleton Lake. You can kind of see the local topography also has this sort of distinctive shape that strongly suggests this is an impact crater. So you can see the outline of the lake and where some of the magnetic highs are. So here we're using magnetics, but you can also use gravity to sort of detect these kinds of structures. So in Ontario, because of the nature of the basement rock, we actually do find a lot of these impact structures: Sudbury, Wanapite, Brett, Holliford, not quite so much, but certainly potentially Skeleton and Charity Shoal also have these very distinctive magnetic signatures. So this is sort of what we know about some of these impact structures. Because the Canadian Shield is such old rock, this is why you have these preserved for such long time periods of hundreds of millions, if not, in the case of Sudbury, almost 2 billion years, which is why sort of Ontario and Quebec are known to have quite a few of these impact structures. Quebec almost actually has quite a few that are known as well. So if you're looking for more information, there are a number of websites. I believe they're going to make them available through the YouTube somehow. The Earth Impact Database and the Western Database both have sort of complete listings of all the recognized ones. There are a couple here that I really enjoy playing around. These are impact simulators, so you can go in it and sort of play around with the size of the asteroid and calculate what kind of effect it would have on Earth when it hits, which is kind of lots of fun to play with. And of course, the Lunar and Planetary Institute down in the US also has a number of resources on impact craters if you're sort of looking for more information. So at this point then, I think I will turn it back over to Nakul, and I'd be happy to answer any questions that people want to bring up. So I will stop the sharing here. So. Okay.
Thank you so much for your wonderful presentation, Professor. And now me and my colleagues would like you to ask you some questions, and I'm going first with my questions. So my first question is, what created an interest for you to do your research in impact structure?
Well, impact structures, as I said, are kind of that boundary between astronomy and geological sciences, and my master's was in physics and astronomy, and I also had sort of a strong interest in geology, geophysics. So, you know, when impact structures came up as a possible project for my PhD thesis, this is really, I think, what got me interested, because it seemed to have elements of both of those things that I found very interesting.
That's really amazing to hear from you, Professor. And my next question is, where do most of the impact structures can be found in Ontario, especially in which part?
Yeah, so the known ones are more in the southern end of Ontario. The truth of the matter is, if you look at the moon, you know there are an awful lot of impacts, right? The impact we know in Ontario, it's not because any area was hit preferentially. It has more to do with, after the fact, where would the geological processes and things of that nature tend to preserve these structures. So in the case of something like Brent or Holliford and potentially Charity Shoal, what's happened is, because these areas were later covered with limestone or other rock, the underlying crater was preserved, and then later some of these rock layers are removed, but you can still see the substance of the crater. So the truth of the matter is, probably most of Earth gets hit on a regular basis. It's just a little bit by geological coincidence that some of these structures survive in a particular sort of geological setting. Because again, Ontario and Quebec have some very old basement rock, most people think of as the Canadian Shield. This is sort of the ideal place for us still to find craters here on Earth.
That's really great to hear, Professor. And I'm passing over to my colleague, Camilla, right now. Here you go, Cam.
Thank you, Professor, for your presentation. My first question is, what's your favorite impact structure in Ontario and why?
Well, that's an interesting question, actually. Sudbury is fascinating simply because it really shows, I think, how the impact interacts with the Earth geology and creates sort of that specific mining resource. But I also really find Charity Shoal, which is a suspected impact crater, kind of fascinating because it's been discovered so recently. It's only in the last sort of 25 years that they recognize the potential for another impact structure to be there, even though, you know, like they've been looking for these things for, you know, Ontario had been surveyed for decades, but it wasn't until you had this sort of better bathymetry and then better magnetics that you could actually potentially identify it as an impact crater.
That's really interesting, actually. I have a second question, which is, in comparison to other countries, how probable do you believe there will be another found of crater impact in Ontario?
So impacts are not impacts when they hit Earth. It's simply a case of the orbital characteristics of the asteroid interacting with Earth. Ontario has as much chance of being hit as anywhere else on Earth. If you look at cratering rates, the potential for an impact exists at any time. With Space Watch, we now have a much better sense of roughly when these things may hit. Where exactly they'd hit on Earth would still really rely on a lot of very fine detail that would be much harder to predict. But even, you know, nowadays we do see small impacts on Mars and the Moon as they occur. Larger impacts are much more rare, happening only every few tens of thousands, hundreds of thousands of years. So for a large impact to hit, you know, may not happen in our lifetimes, but eventually it's going to happen again.
Thank you for answering my question. It was really interesting. I am now passing it to Maheen. She's going to ask questions too.
Thank you for the great talk. So I just have two questions. The first question is, how do the characteristics of a crater change over time, if it does?
Oh, they very definitely do. So if you look at sort of impact craters in the Moon, you can see there's a distinct raised rim. And if it's a larger complex crater, you have that upraised structure in the middle. Earth is a very active planet. We have weathering, we have running water, we have weather, we have plate tectonics, we have volcanoes. So over time, just through normal weathering processes, the rim of the crater will slowly be eroded down. So the rim will disappear. The bowl will tend to fill in because sediments will sort of move to that lower place. And Earth should probably have many, many more craters than it does. But over time, all these processes will slowly erode away. So you end up with things like Holliford, because if you looked at Holliford and you drove through it, because there are roads that go right through the crater, you might not realize you're in an impact crater, simply because there's vegetation, it's been covered in later rock. But if you look around, you can actually see the bowl of that crater. So they do wear away over time, simply because Earth is such an active environment. This happens on other planetary bodies too, but because you don't have vegetation, you don't have plate tectonics, you don't have as much active volcanic activity, it happens much more slowly.
It's interesting to know it's different for different planets. Following up to your to the question I just asked, if there are changes in the characteristics, can they provide evidence of past geological events on a planet?
Very, very much so. If we look on Mars right now, there are impact structures that distinctly, you have that distinct raised rim. And what you see when you look at the impact structure is you'll see the rim will have what we call a breach, because far in Mars past, of course, with water in the surface, these craters potentially filled with water. And then as it fills with water, it breaches the rim where it's weak and the water flows out. So you get what we call rim breaches, where you have a gap in the rim where the water has flowed out. We've seen a bit of detail like this when I model the subsurface structure of Holliford and Charity Shoal as well. But certainly on Mars, we see evidence of water weathering. Gustav crater on Mars distinctly, and Jezero crater distinctly are known to have deltaic type structures. In this case, though, the water actually flowed into the low ground and deposited deltas, much the way that deltas are deposited at the mouths of rivers like the Amazon or the Nile, or any of those major river structures on Earth. Right, so we do see that kind of activity, particularly on Mars, because Mars has had this kind of water flow in the past.
That's very interesting. It means craters aren't really a bad thing. I will now hand it over to Pouria to ask some questions. Take it away, Pouria.
Thank you so much, Maheen. And thank you so much, Doctor, for your your presentation. It was very informative. And I was thinking, like, is there a category for craters, and how do you categorize them?
That really goes back to that slide I had earlier of simple and complex. If you get into really big impact structures, places like the moon, you'll also get what you call multi-ring basins, where it may actually, there's some speculation that some of these really big impacts actually ruptured the crust and allowed magma to flow in, creating sort of a magma pool within the crater that hardens into igneous rock. So the main types are those simple, which are smaller, just a simple bowl, complex impact structures that will then have an uplift. And as the complex get bigger and bigger, you will also see sort of not just a single outer ring, but sort of a series of rings within the crater basin. Chicxulub is known to have these kind of inner rings. Other structures, certainly on the moon and Mars, show evidence of these kind of multi-ring structures. They get bigger and bigger until you get to these sort of massive basins.
Mm-hmm. Thank you very much. And so, as my next question, what is the greatest mystery in the science of geophysics?
Geophysics is a big field. There's a great deal of science that's done that's described as geophysics. So there are many things you could call mysteries. So, I mean, geophysics, the kind of thing I do in and of itself is not necessarily a specific discovery. It's using our understanding of gravity, of seismic, of magnetics to probe, whether it's at the near surface or deeper into the Earth. So it's applying a technique to study various kind of things. So it's not really something where a big mystery comes into play. But there are a lot of things that we've detected with geophysics that we really aren't quite sure what exactly they are, because we haven't necessarily seen that signal somewhere else.
Mm-hmm. I guess. See, thanks so much. Yeah, I had this question in my mind because, like, in astronomy and physics, the biggest mystery for now, one of them is the dark matter and dark energy. I was thinking maybe there is another mystery in the science of geophysics.
Yeah, it's not quite the same thing. I mean, geophysics covers so many areas. That's why geophysics can refer to elements of plate tectonics and how plate tectonics work. And there are certainly quite a number of questions about plate tectonics that remain unanswered. If you're talking about one that has sort of a major effect, plate tectonics and how exactly they, why exactly earthquakes happen when they would, I'd have to say that was probably one of the ones that comes up the most often when people are asking about sort of the physical nature of Earth and the physics of what is going on, because it's just such a complex system. It's hard to know, for example, like when those physical points where an earthquake will occur and where the plates sort of go through that sudden motion will actually happen.
Got it. Thank you so much, Professor, for your informative slideshow.
All right, so before we head on towards the outro, I would like to say that thank you so much, Dr. Armour, for joining us tonight and answering all the questions. It was a pleasure to have you on. Well, everyone, you have been listening to the Alumni Carswell Observatory's weekly Teletube broadcast, the online astronomy and astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Cam, Nakul, Pouria, and myself, Maheen. Make sure to leave any comments or questions in the comment section of the video and talk to us in the chat right now. All of our programs are free, but if you would like to make a donation, see our website at yorku.ca/science/observatory/. You can always connect with us on Twitter with the handle @YorkObservatory and check out our website for show notes, content, updates, and contact info at yorku.ca/science/observatory/. Thanks for tuning in. Clear skies and have a good night.